Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to get comfortable, to let the day fall away, to simply be here. Where in the world are you watching from? A quiet bedroom where the stars might be visible through your window. A cozy corner where you can finally rest. Wherever you are, you're exactly where you need to be. Tonight we're going to explore something truly remarkable. The Andromeda Galaxy, our nearest large galactic neighbour, is heading toward us, and recent discoveries have revealed that it's far bigger than we ever imagined. We'll discover how scientists first realised this collision was inevitable, understand what happens when galaxies merge, and contemplate what this means for our cosmic future. It's a journey that spans billions of years, across distances so vast they challenge imagination itself. But don't worry, this isn't going to be a story of catastrophe or cosmic destruction. Instead, we'll move slowly and carefully through one of the most beautiful processes in the universe, taking our time with each discovery. We'll see how galaxy collisions create new stars, how they're happening everywhere we look, and how the one approaching us won't arrive for billions of years. By the end, I think you'll find this cosmic dance more peaceful than alarming, more wondrous than worrying. If you enjoy these calm explorations of the universe, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being here, for sharing these cosmic journeys with me. So settle in, let your shoulders drop, take a slow breath, and let's begin our slow drift through the story of Andromeda's approach. Through the gentle collision of galaxies through billions of years of cosmic time, there's nowhere you need to be right now, nothing you need to do, just listen and let the story unfold. The universe has been here for nearly 14 billion years. It can wait while you rest. On a dark night, far from city lights, you can see it with your naked eye. A small, fuzzy patch of light in the constellation Andromeda. To the untrained eye, it looks like nothing special. Perhaps a distant star cluster. Perhaps a nebula, something small and nearby. But that smudge of light is something almost incomprehensibly vast. It's the Andromeda Galaxy, catalogued as Messier 31, a spiral galaxy containing perhaps 1 trillion stars. When you look at that faint glow, you're seeing light that has travelled 2.5 million years to reach your eyes. The light you're seeing tonight left Andromeda when our ancestors were just learning to use stone tools, when the genus Homo was young on the plains of Africa. For most of human history, we didn't know what that smudge was. Ancient astronomers noted it, of course. The Persian astronomer Al-Sufi described it in the year 964, calling it a small cloud. Chinese astronomers had recorded it centuries earlier. But they thought it was something within our own cosmic neighbourhood, a nearby phenomenon, close enough to touch if we could only reach high enough. Even through early telescopes, Andromeda remained mysterious. It showed structure, yes, a bright core surrounded by a glowing disk. But what was it? Some astronomers thought these spiral nebulae, as they were called, were simply clouds of gas within our own galaxy, places where new solar systems might be forming. Others suspected something grander, something more distant. The truth wouldn't be revealed until the 1920s, when a young astronomer named Edwin Hubble turned the most powerful telescope in the world toward that ancient smudge of light. What he discovered changed everything we thought we knew about the universe. He found that Andromeda wasn't a small cloud within our galaxy. It was a galaxy itself, an entire island universe of stars, as vast as our own Milky Way. And it was moving. The universe, we were about to discover, was far stranger and more dynamic than we'd ever imagined. That peaceful smudge of light, that gentle glow in the night sky, was hurtling through space at hundreds of kilometers per second, and it was coming our way. To understand what Andromeda truly is, we need to step back and contemplate what a galaxy actually means. It's a word we use casually now, tossed around in science fiction and astronomy documentaries. But the concept is almost overwhelming when you really stop to consider it. A galaxy isn't just a collection of stars. It's a vast cosmic structure, a gravitationally bound system containing stars, stellar remnants, interstellar gas, dust, and dark matter, all swirling together in an intricate dance that has lasted for billions of years. Our Milky Way galaxy contains somewhere between 200 billion and 400 billion stars. That's a number so large it becomes meaningless in human terms. We can write it down, we can say it out loud, but truly grasping what it means is almost impossible for our minds, which evolved to understand things like the number of apples in a basket or people in a village. If you tried to count every star in our galaxy, spending just 1 second on each, it would take you more than 12,000 years to finish. You'd need to start counting in the time before the first pyramids were built, and continue without pause until today, and you still wouldn't be done. And our galaxy is just one of perhaps 2 trillion galaxies in the observable universe. 2 trillion separate island universes, each containing billions or even trillions of stars of their own. Each of these galaxies is an island of stars, gas, and dust. Held together by gravity and spinning through the darkness of space like cosmic pinwheels or glowing spheres suspended in an ocean of darkness. They come in different shapes and sizes, a cosmic menagerie of forms that astronomers have spent decades cataloguing and studying. Spiral galaxies like our own, and Andromeda, with graceful arms wound around a bright core, their structure resembling hurricanes frozen in time and space. Elliptical galaxies, shaped like cosmic eggs or footballs. Smooth and featureless, containing mostly older reddish stars and little of the gas needed to form new ones. Irregular galaxies, with no particular structure at all, often distorted by gravitational interactions with their neighbours, or still forming from primordial gas clouds. And dwarf galaxies, small collections of stars orbiting larger companions, sometimes containing only a few million stars compared to the hundreds of billions in their giant neighbours. Between these islands lies mostly emptiness. The space between galaxies is called the intergalactic medium, and it's a void unlike anything we experience on Earth. It's not just empty in the sense of a vacant room or a desert. It's a darkness so profound, a vacuum so complete, that it defies our everyday understanding of what emptiness means. If you were floating in intergalactic space, millions of light years from the nearest galaxy, the nearest star would be so far away it would be invisible to the naked eye, its light too faint and too distant to register on your retina. You'd be surrounded by absolute darkness, unable to see even the galaxies around you, except as the faintest smudges of light, barely distinguishable from the cosmic background radiation that fills the universe. No sound, no light, no warmth. Just you and the void, separated from everything by distances that make astronomical units seem like inches. But galaxies aren't quite as isolated as they might seem. They influence each other across these vast distances, their gravitational fields reaching out like invisible hands. Gravity doesn't care about emptiness. It doesn't need a medium to propagate through. It reaches across millions of light years, pulling galaxies into groups and clusters, creating vast cosmic structures that span hundreds of millions of light years. These structures form a cosmic web, with galaxies clustered along filaments of dark matter, separated by enormous voids where almost nothing exists. The universe, when viewed at the larger scales, looks almost organic, like neural pathways in a brain, or the microscopic structure of foam. Our Milky Way belongs to what astronomers call the local group, a collection of more than 80 galaxies bound together by gravity, a cosmic family held in mutual gravitational embrace. Most of these are small dwarf galaxies, containing a few billion stars at most, tiny companions that orbit the larger galaxies like moons orbit planets. Some of these dwarfs are being slowly torn apart by tidal forces, their stars stripped away and absorbed into their larger neighbours, a process that will eventually erase them entirely. but the local group has three large galaxies, three dominant members that shape the gravitational architecture of our cosmic neighbourhood. The Milky Way, our home, a barred spiral galaxy that we can never truly see from the outside. The Andromeda Galaxy, the largest member of the group, visible to the naked eye on dark nights as a faint smudge in the constellation it's named after. And the Triangulum Galaxy, smaller than the other two but still impressive in its own right, containing perhaps 40 billion stars and located about 3 million light-years from Earth. And here's what makes our story interesting. What transforms this from a simple catalogue of cosmic objects into a narrative with tension and inevitability? In this cosmic neighbourhood of ours, Andromeda is the largest resident. It's more massive than the Milky Way, probably containing somewhere between 800 billion and 1 trillion stars compared to our few hundred billion. It contains more stars, spans a larger volume of space, and dominates the gravitational landscape of the local group. Its gravity shapes the orbits of the smaller galaxies around it, determines the motion of gas clouds in the intergalactic medium, and reaches across the millions of light-years that separate it from us, which means, inevitably, inexorably, that its gravity is pulling on us, has been pulling on us for billions of years, drawing us closer with each passing moment. We are falling toward Andromeda, and Andromeda is falling toward us, and nothing in the universe can stop what's coming. How do you measure the distance to something so far away that light takes millions of years to cross the gap? It's a question that puzzled astronomers for decades, a problem that seemed almost impossible to solve. The breakthrough came from a peculiar type of star called a Cepheid variable. These stars pulse in brightness, growing brighter and dimmer in regular cycles that can last from days to months. And here's the remarkable thing that astronomer Henrietta Swan-Leavitt discovered in the early 1900s. The period of a Cepheid's pulsation is directly related to its true brightness. A Cepheid that pulses slowly is much brighter than one that pulses quickly. This discovery gave astronomers a cosmic measuring stick. If you could find a Cepheid variable in a distant galaxy, measure how long it took to pulse, you could calculate its true brightness. And if you knew its true brightness and could measure how bright it appeared from Earth, you could calculate its distance. It was elegant, it was precise, and it changed astronomy forever. Edwin Hubble used this technique when he pointed the Mount Wilson telescope at Andromeda in the early 1920s. He found Cepheid variables in what was then called the Andromeda Nebula. He measured their pulsation periods, he calculated their true brightness, and then he worked out the distance. The number he arrived at was shocking. Andromeda wasn't thousands of light years away. Inside our own galaxy, it was nearly 1 million light years distant, completely separate from the Milky Way. We now know Hubble's calculation was off. That better measurements place Andromeda at about 2.5 million light years from us. But his fundamental conclusion was correct. The universe was vastly larger than anyone had imagined, but measuring distance was just the beginning. Astronomers also wanted to know how Andromeda was moving. Was it sitting still in space, drifting slowly in some random direction? The answer came from studying the light itself. When an object moves toward or away from us, the wavelengths of light it emits get compressed or stretched. If it's moving toward us, the light shifts toward the blue end of the spectrum. If it's moving away, it shifts toward red. By measuring this Doppler shift in Andromeda's light, astronomers discovered something unexpected. Most galaxies we observe are moving away from us. Their light shifted toward red as they recede into the expanding universe. But Andromeda's light was shifted toward blue. It was moving toward us, approaching at about 110 kilometers per second. Not quickly by cosmic standards, but relentlessly, inevitably, drawing closer with each passing year. And this raised an obvious question. If Andromeda is approaching us, will it eventually reach us? The answer, we've now confirmed through decades of careful measurement, is yes. Andromeda and the Milky Way are on a collision course. When scientists first confirmed that Andromeda was approaching, there was uncertainty about what would happen. Would the two galaxies pass by each other like ships in the night, their paths crossing but never truly meeting? Or would they collide? The challenge was that measuring the velocity of Andromeda's approach only told us part of the story. We knew it was coming closer, but we didn't know if it was heading straight for us or passing by at an angle. Imagine watching a car approaching in the distance. You can tell it's getting closer, but you can't tell if it's going to hit you or swerve past at the last moment. We needed to measure not just Andromeda's radial velocity, how fast it was approaching, but also its tangential velocity, how fast it was moving sideways across the sky. This measurement required incredible precision. Andromeda is so far away that its sideways motion across the sky is almost imperceptibly small. Even moving at hundreds of kilometers per second, it takes thousands of years for Andromeda to shift position noticeably against the background stars. No telescope in the early 20th century could measure such tiny movements. But by the early 2000s, we had the Hubble Space Telescope, capable of measuring positions with extraordinary accuracy. Astronomers used Hubble to observe specific stars in Andromeda, then waited years and observed them again. By comparing the positions of these stars over time, they could detect Andromeda's sideways motion. The results, published in 2012, were definitive. Andromeda isn't passing by. It's heading almost directly toward us. Oh, it has some sideways motion, yes. The collision won't be perfectly head-on, but the two galaxies are absolutely going to merge. There's no uncertainty anymore, no possibility of a near miss. The fate of the Milky Way and Andromeda is sealed. The timeline, based on current measurements and computer simulations, goes something like this. In about 4 billion years, Andromeda will be close enough that it will dominate the night sky, no longer a small smudge, but a vast band of light stretching across the heavens. In about 4.5 billion years, the two galaxies will make their first pass through each other, their spiral arms beginning to distort and stretch. But galaxy collisions aren't simple. They don't merge on the first pass. Instead, the two galaxies will swing past each other, pulled apart again by their momentum, only to fall back together under gravity's relentless pull. They'll collide again and again. Over the course of about 2 billion years, the Milky Way and Andromeda will engage in a cosmic dance, passing through each other multiple times, each collision more chaotic than the last. And finally, about 6 billion years from now, the merger will be complete. Where there were once two galaxies, there will be one. A new galaxy, shaped by the collision. Likely an elliptical galaxy rather than the spiral forms we know today. Astronomers have even given this future galaxy a name. They call it Milkomeda. The word collision sounds violent, doesn't it? It conjures images of destruction, of catastrophic impact. But galaxy collisions are something gentler, something stranger than anything in our everyday experience. When two galaxies collide, they don't smash into each other like cars in an accident. They pass through each other, interpenetrating, their stars threading between each other like two swarms of fireflies meeting in the night. And here's the remarkable thing. Despite containing billions of stars each, the galaxies are mostly empty space. The distances between stars are so vast that actual stellar collisions are extraordinarily rare. Think about it this way. The nearest star to our Sun, Proxima Centauri, is about 4 light-years away. That's about 40 trillion kilometers. If the Sun were the size of a grain of sand, Proxima Centauri would be another grain of sand 8 kilometers away. Now imagine 2 handfuls of sand, grains scattered across distances of kilometers, passing through each other. The chances of any 2 grains actually touching would be infinitesimally small. That's what happens when galaxies collide. The stars pass by each other, occasionally coming close enough to perturb each other's orbits, but almost never actually colliding. Our Sun, with its family of planets, will almost certainly emerge from the collision unscathed by direct impact. But that doesn't mean nothing happens. The collision might not destroy individual stars, but it transforms the galaxies themselves. The gravitational interactions between billions of stars create tidal forces, vast pulls and tugs that stretch and distort the galaxy's shapes. Spiral arms get pulled out into long streamers. Stars get flung into new orbits. Some stars might even be ejected from the galaxies entirely, thrown out into the intergalactic void. And then there's the gas. Galaxies contain not just stars, but enormous clouds of gas and dust. When galaxies collide, these clouds smash into each other, and unlike the stars, they do collide directly. The collision compresses the gas, heating it, causing it to collapse under its own gravity, and when gas clouds collapse, they form new stars. This is where galaxy collisions become creative rather than destructive. They trigger waves of star formation, creating millions or even billions of new stars in a relatively short period. The collision of the Milky Way and Andromeda will likely spark the birth of countless new suns, new stellar systems, perhaps even new planets. We've observed this process in other colliding galaxies throughout the universe. Through powerful telescopes, we can see galaxies in various stages of merger, their spiral structures distorted, brilliant blue regions marking areas of intense star formation. These collisions are laboratories where we can study what will happen to our own galaxy billions of years in the future. And perhaps most beautifully, these collisions show us that change in the universe doesn't mean ending. It means transformation. The Milky Way as we know it will cease to exist. Andromeda as we know it will cease to exist. But something new will be born, a new galaxy containing all the stars of both its parents, a cosmic phoenix rising from the merger of two ancient spiral galaxies. For decades, astronomers thought they understood Andromeda's size. Based on observations of its visible light, the galaxy appeared to span about 220,000 light-years across. Impressive, certainly. Larger than our own Milky Way, which stretches about 100,000 light-years from edge to edge. But the difference didn't seem dramatic. Then, in the early 2000s, astronomers began studying Andromeda in new ways, looking not just at its stars but at the faint halo of gas surrounding it. What they discovered was astonishing. Andromeda was far larger than anyone had imagined. Using spectroscopic techniques to detect extremely faint gas clouds, astronomers traced Andromeda's outer regions far beyond where its visible stars end. They found gas clouds, still gravitationally bound to Andromeda, extending out to distances of nearly 1 million light-years from the galaxy's centre. That's about half the distance between Andromeda and the Milky Way. Let that sink in for a moment. Andromeda's outer envelope reaches halfway to our galaxy. We're not just approaching Andromeda. In a very real sense, we're already touching it. The outermost wisps of Andromeda's gas halo might already be mingling with the outer reaches of the Milky Way's own halo. But the revelations about Andromeda's size didn't stop there. In 2020, astronomers using data from the Hubble Space Telescope made an even more startling discovery. They found that Andromeda's halo wasn't just big. It was enormous, extending out to at least 1.3 million light-years and possibly as far as 2 million light-years. If this measurement is correct, if Andromeda's halo really does extend 2 million light-years from its centre, then the distance between Earth and Andromeda's centre is only about 500,000 light-years more than Andromeda's radius. We're well within Andromeda's sphere of influence, embedded in its outer gravitational embrace. The halo itself is a marvel. It's made of extremely hot gas, plasma heated to temperatures of hundreds of thousands of degrees. But it's also incredibly thin, containing only about 1 atom per cubic centimetre. If you were floating in Andromeda's halo, you'd experience it as a perfect vacuum, indistinguishable from the emptiness of intergalactic space. Yet despite its thinness, the halo contains tremendous mass. Astronomers estimate that Andromeda's halo holds as much mass as all the gas in the visible disk of the galaxy, perhaps even more. It's a vast reservoir of material, left over from Andromeda's formation, enriched by elements forged in ancient supernovae and blown out from the galaxy's core by stellar winds and black hole activity. This discovery changed our understanding not just of Andromeda but of galaxies in general. If Andromeda has such an enormous halo, our Milky Way likely does too. The visible parts of galaxies, the parts we can see in photographs, are just the bright cores of much larger structures. Galaxies extend far beyond where their stars end, reaching out into the darkness with invisible fingers of gas. But the gas halo, as vast as it is, isn't the largest component of Andromeda. There's something else surrounding the galaxy, something even more extensive and far more mysterious, something we can't see at all. Dark matter remains one of the deepest mysteries in modern astronomy. We can't see it. It doesn't emit light. It doesn't absorb light. It doesn't interact with the electromagnetic radiation in any way we can detect. And yet we know it's there, can measure its presence through the gravitational effects it produces. The first hints of dark matter came in the 1930s, when astronomer Fritz Zwicky noticed that galaxies in the Coma cluster were moving far too fast for the amount of visible matter present. The cluster should have flown apart long ago. Something invisible was providing extra gravity, holding the galaxies together. In the 1970s, astronomer Vera Rubin made similar observations of individual galaxies, including Andromeda. She measured how fast stars were orbiting at different distances from the galactic centre. According to the laws of gravity, stars farther from the centre should orbit more slowly, just as outer planets in our solar system orbit more slowly than inner planets. But that's not what Rubin found. Stars at the edge of Andromeda were moving just as fast as stars closer to the centre. The only explanation was that there must be far more mass than we could see, distributed in a vast halo around the galaxy, providing the extra gravity needed to keep those outer stars moving so quickly. We now believe that Andromeda, like all large galaxies, is embedded in a halo of dark matter that extends far beyond its visible boundaries. This dark matter halo might stretch for hundreds of thousands of light years, perhaps even millions of light years. It contains far more mass than all the stars and gas in Andromeda combined. What is dark matter? We don't know. It's not made of atoms like the matter we're familiar with. It might be composed of exotic particles that interact only through gravity, particles that pass through normal matter like ghosts passing through walls. Physicists have proposed numerous candidates, particles with names like WIMPs and axions and sterile neutrinos. But despite decades of experiments, we haven't directly detected dark matter particles yet. What we do know is that dark matter makes up about 85% of all matter in the universe. Everything we can see, all the stars and galaxies and nebulae, all the planets and dust and gas, represents only about 15% of the matter that exists. The rest is dark, invisible, known only through its gravitational influence, and when Andromeda and the Milky Way collide, their dark matter halos will collide too. Or rather, they'll pass through each other, since dark matter particles don't interact even with each other except through gravity. The collision will redistribute the dark matter, creating a new, larger halo around the merged galaxy. Computer simulations of the collision take dark matter into account, modelling how its gravity will affect the merger. And what they show is that dark matter plays a crucial role, its invisible presence guiding the dance of visible matter, shaping the final form of the merged galaxy. We live in a universe where most of what exists is invisible, where darkness holds the light together. Galaxies don't float through empty space randomly, like leaves drifting on a still pond. They're caught in currents, flows of matter driven by gravity on the largest scales imaginable. To understand why Andromeda is approaching us, we need to understand these cosmic rivers. When we look at the distribution of galaxies across the universe, we see structure. Galaxies aren't spread evenly through space. Instead, they're arranged in vast filaments and sheets, surrounding enormous voids where few galaxies exist. This cosmic web, as astronomers call it, was created by gravity acting on slight density variations in the early universe. In regions where matter was slightly denser than average, gravity pulled in more matter, creating even denser regions. Over billions of years, this process created filaments of dark matter stretching across hundreds of millions of light years. Galaxies formed along these filaments, like cities along a river, clustered together in the densest regions. Our local group, containing the Milky Way and Andromeda, sits at the intersection of several smaller filaments. We're part of a larger structure called the Laniakea supercluster, an enormous region of space about 500 million light-years across, containing the mass of about 100,000 trillion suns. But even within this structure, there are flows and currents. Galaxies don't just sit still. They're pulled by the gravity of dense regions and pushed by the expansion of the universe in underdense regions. The result is a complex pattern of motion, with galaxies streaming along filaments toward gravitational attractors. The Milky Way and Andromeda are both part of the same gravitational system, the local group, and within this system, Andromeda is the dominant mass. Its gravity has been pulling on the Milky Way for billions of years, gradually drawing us together. We're like two dancers caught in each other's gravitational embrace, spiralling slowly inward toward an inevitable meeting. But it's not just Andromeda's gravity affecting us. The entire local group is falling toward a massive cluster of galaxies called the Virgo cluster, about 50 million light-years away. This cluster contains thousands of galaxies and exerts a gravitational pull on everything in our cosmic neighbourhood. Our motion through space is a combination of our orbit within the local group and our fall toward Virgo. And Virgo itself is part of an even larger flow, a vast river of galaxies streaming toward an enormous gravitational anomaly called the Great Attractor. And beyond that, toward an even more massive structure called the Shapley supercluster. Motion in the universe is nested, each smaller motion embedded within larger flows, like eddies within currents within rivers. When we say Andromeda is approaching us at about 110 kilometers per second, that's the velocity we measure relative to the Milky Way. But relative to the cosmic microwave background radiation, the afterglow of the Big Bang that fills all of space, our local group is moving at about 600 kilometers per second. We're part of a much faster flow, a cosmic current carrying us through the universe. Understanding these motions gives us perspective. Andromeda isn't special in approaching us. Everything in the universe is moving, pulled by gravity, pushed by expansion, caught in flows that span billions of light-years. The collision of Andromeda and the Milky Way is just one small event in a universe full of motion. How do we know what will happen when Andromeda and the Milky Way collide? We can't wait 4 billion years to observe it. Instead, we run simulations, using computers to model the merger and predict its outcome. These simulations are marvels of modern astronomy. They begin with the known properties of both galaxies, their masses, their shapes, their rotation rates, their approach velocity. Then they apply the laws of physics, calculating how gravity will affect every component of both systems over billions of years. Early simulations, run in the 1970s and 80s, were relatively simple. They modelled galaxies as collections of thousands of particles, each representing millions of stars. The computers of that era could barely handle such calculations, taking days or weeks to simulate a single collision. Modern simulations are far more sophisticated. They can model hundreds of millions of particles, representing not just stars but also gas clouds and dark matter. They account for complex physical processes. Star formation triggered by colliding gas clouds, stellar winds from massive stars, energy output from supernovae, feedback from supermassive black holes. One of the most detailed simulations of the Milky Way-Andromeda collision was published in 2012 by astronomers using NASA's supercomputers. This simulation modelled the collision at extremely high resolution, tracking individual regions of both galaxies as they merged over billions of years. The simulation confirmed what astronomers had long suspected. The first encounter would occur in about 4 billion years. Andromeda's gravity would begin distorting the Milky Way's spiral arms, pulling stars into elongated tidal tails. The two galaxies would swing past each other, then fall back together for a second collision about 500 million years later. With each encounter, the galaxies would become more distorted, their beautiful spiral structures gradually destroyed. Stars would be scattered into chaotic orbits. Some would be flung far from the merging galaxies, thrown out into intergalactic space. Others would sink toward the centre, drawn inward by gravitational interactions. After about 2 billion years of this chaotic dance, the merger would be complete. The simulation showed that the final product would likely be an elliptical galaxy, with stars orbiting in random directions rather than the orderly rotation of a spiral. All the graceful structure would be gone, replaced by a more uniform egg-shaped distribution of stars. But the simulation also revealed something surprising about our solar system's fate. The Sun, currently located about 26,000 light-years from the Milky Way centre, would likely be flung to the outer regions of the merged galaxy. In the simulation, our solar system ended up about 40,000 light-years from Milkomeda's centre, a quiet suburban location in the new galaxy. The simulation even predicted what someone on Earth would see during the collision. In about 4 billion years, Andromeda would no longer be a faint smudge but a spectacular band of light across the sky, perhaps as bright as the Milky Way appears to us now. During the closest encounters, the two galaxies would fill the night sky with complex, swirling patterns of stars and dust. Of course, simulations are only as good as our understanding of the physics involved. Each new discovery about galaxies, about dark matter, about how stars form and evolve, leads to more refined simulations. The story of the collision gets updated and improved with each iteration, yet the fundamental conclusion remains unchanged. We know the collision will happen, we know approximately when, and we know it will fundamentally transform both galaxies, creating something new from the merger of these two ancient stellar islands. The collision between the Milky Way and Andromeda might sound unique, but it's not. Everywhere we look in the universe, we see galaxies colliding, merging, interacting. It's one of the fundamental processes by which galaxies grow and evolve. In fact, most large galaxies have grown through mergers. Our Milky Way bears the scars of past collisions, traces of smaller galaxies it has consumed over billions of years. Astronomers have identified stellar streams, long ribbons of stars stretched out across the sky, that are the remnants of dwarf galaxies torn apart by the Milky Way's gravity. One of these victims is called the Sagittarius Dwarf Elliptical Galaxy. It's currently being ripped apart as it orbits through the Milky Way's disk. Its stars are being scattered, incorporated into our galaxy. In a few 100 million years, it will be completely destroyed, its stars indistinguishable from the Milky Way's own, and there's evidence of much larger past collisions. Some astronomers believe that about 10 billion years ago the Milky Way merged with another large galaxy, an event that fundamentally shaped our galaxy's structure. The thick disk of old stars surrounding the Milky Way's thinner disk might be the remnant of this ancient collision. But we don't need to look to the past to see galaxy mergers. They're happening right now, all across the universe. Through powerful telescopes, we can observe galaxies in every stage of the merger process. Some are in the early stages, two distinct spiral galaxies beginning to distort each other's shapes with their gravity. Others are in the middle of violent encounters, their spiral structures completely disrupted, brilliant blue regions marking areas where gas clouds have collided and triggered waves of star formation. Still others are nearly finished, their merger almost complete. The last remnants of separate structure fading away. Astronomers have catalogued hundreds of interacting galaxy pairs. They've studied how the merger rate changes over cosmic time, finding that collisions were more common in the early universe when galaxies were closer together. They've discovered that major mergers, collisions between galaxies of similar size, often trigger the formation of massive elliptical galaxies. One of the most important discoveries is that galaxy mergers don't just rearrange stars, they can fundamentally change a galaxy's evolution. The collision of gas-rich galaxies can trigger enormous bursts of star formation, using up a galaxy's gas reservoir in a relatively short time. Some of the most luminous galaxies in the universe are merger systems caught in the midst of these star formation episodes. Mergers can also affect the supermassive black holes at galactic centres. When two galaxies merge, their central black holes eventually sink to the centre of the new galaxy and merge as well, creating an even more massive black hole. This merger might trigger a phase of intense activity, with the black hole consuming vast amounts of material and shining as a brilliant quasar. By studying these ongoing collisions across the universe, astronomers have learned what to expect from our own impending merger. The Andromeda Milky Way collision won't be unique. It will follow patterns we've observed countless times before. And that gives us confidence in our predictions, in our simulations, in our understanding of what the future holds. We're watching the universe's grand recycling program in action, galaxies combining and recombining, growing larger through cosmic cannibalism, transforming and evolving across billions of years. Let's try to picture it, the timeline of the approaching collision laid out before us like a cosmic calendar. Right now, in our present moment, Andromeda is 2.5 million light-years away. The light we see from it tonight left that galaxy when our ancestors in Africa were just beginning their long, evolutionary journey toward modern humans. In 1 billion years from now, Andromeda will still appear much as it does today. Perhaps slightly larger in the sky, but not dramatically different. Someone looking up from Earth in 1 billion years, if there are still humans or their descendants watching the stars, would see a familiar constellation pattern, a familiar smudge of light in the same general location. But things are happening, slowly but inexorably. With each passing million years, Andromeda draws about 100,000 kilometers closer. It doesn't sound like much, not compared to the vast distance still separating us. But it adds up, steadily, patiently, as the eons pass. 2 billion years from now, the difference becomes noticeable. Andromeda begins to look larger in the night sky, no longer just a faint smudge, but a definite oval of light. Its central bulge becomes visible to the naked eye. The galaxy's approach is becoming undeniable. 3 billion years in the future, Andromeda dominates the night sky. It's grown from a small fuzzy patch to a magnificent band of light stretching across several degrees of sky. If you were standing on Earth, looking up on a dark night, you'd see Andromeda's spiral structure with your naked eyes, its lanes of dark dust silhouetted against glowing clouds of stars. And then comes the critical period, the window between 3.5 and 4 billion years from now. During this time, Andromeda swells rapidly in apparent size. What was once a distant neighbour becomes an enormous presence overhead. The galaxy grows week by week, month by month, spreading across the sky like a cosmic bloom opening. At 4 billion years, Andromeda fills much of the visible sky. Its central bulge glows brilliantly. Its spiral arms stretch in graceful arcs. And for the first time in Earth's history, assuming Earth still exists and retains an atmosphere, the sky is lit not just by one galaxy, the Milky Way, but by two. Andromeda and the Milky Way shine from opposite sides of the sky, each offering a spectacular view of galactic architecture. But Andromeda hasn't stopped moving. It continues to approach, growing larger still. And now something new begins to happen. The two galaxies' outer regions start to interact. Tidal forces, the stretching effects of gravity, begin to distort both galaxies' shapes. The first stars are pulled from their orbits, drawn into elongated streams between the galaxies. About 4.5 billion years from now, Andromeda and the Milky Way make their first pass through each other. Their disks intersect. Billions of stars from each galaxy thread through the space between stars in the other. The night sky becomes a chaos of light, stars from both galaxies visible in every direction, the familiar constellations completely disrupted. And this is just the beginning. The galaxies pass through each other and then, slowed by their mutual gravity, fall back together for another collision, and another. The cosmic dance has begun, and it will continue for billions of years more. What happens to stars during a galaxy collision? It's a question worth contemplating carefully, because the answer is both reassuring and profound. Imagine you're a star in the Milky Way as Andromeda approaches. Perhaps you're a star like our Sun, a medium-sized yellow dwarf with a family of planets orbiting around you. You've been peacefully orbiting the galactic centre for billions of years, following your appointed path through space, unaware of the approaching collision. As Andromeda draws near, you begin to feel its gravity. It's subtle at first, just a tiny additional tug added to the gravitational pull of the Milky Way's billions of other stars. But it grows stronger year by year, decade by decade. Your orbit begins to shift slightly, perturbed by this massive intruder. Then comes the first pass. Andromeda's disk cuts through the Milky Way's disk. Stars from the approaching galaxy stream past you. And here's what's remarkable. Not a single one comes close to you. The nearest might pass several light years away. Most pass hundreds or thousands of light years distant. You sail through Andromeda's disk as smoothly as a mote of dust drifting through a vast empty hall. This is the strange nature of galaxy collisions. Despite containing hundreds of billions of stars, galaxies are mostly empty space. The average distance between stars in our galaxy is about 4 to 5 light years. That's enormous compared to the size of stars themselves. If the Sun were the size of a period on this page, the nearest star would be another period 10 miles away. So when two galaxies collide, their stars pass by each other without touching. Computer simulations suggest that in the entire Milky Way Andromeda collision, perhaps a few dozen stars out of hundreds of billions might actually collide with other stars. The odds of our Sun colliding with another star are so low they're essentially zero, but that doesn't mean nothing happens to you. Even though other stars don't hit you, their gravity affects your orbit. Each star that passes nearby tugs on you slightly, changing your velocity, altering your path. The cumulative effect of billions of such encounters can be dramatic. You might find your orbit becoming more elliptical, carrying you farther from the galactic centre on each circuit, or you might sink inward. Drawn toward the dense core of the merging galaxy, some stars are flung outward with such violence that they escape the galaxy entirely, cast off into the intergalactic void to wander alone forever. And your planets. If you have planets, like our Sun does, they remain safely in orbit around you. The gravitational disturbances from the collision affect stars, not the much smaller scale planetary systems. Your planets continue orbiting, their paths unchanged, while you and your entire solar system are swept along by the galactic merger. There is one genuine danger, though. If your wandering orbit brings you too close to the galactic centre, you might encounter the crowded environment there, where stars are packed much more densely. In the core of a galaxy, stars are close enough that gravitational interactions can be significant. A close encounter with another star might disrupt your planetary system, pulling planets into eccentric orbits or even stripping them away entirely. But for most stars, the collision is remarkably gentle. You're stirred into a new orbit, mixed with stars from another galaxy, but you and your planets emerge essentially unharmed. When the merger is complete and the chaos settles down, you find yourself part of a new galaxy, Milkomeda, orbiting its centre along with 1 trillion other stars, both those who started in the Milky Way and those who came from Andromeda. From the perspective of planets orbiting stars, the collision is almost a non-event, a cosmic reshuffling that rearranges the gallery of stars in the sky, but leaves local physics unchanged. Our Sun has a special significance in this story, of course. It's our star, the centre of our solar system, the source of all energy that powers life on Earth. What happens to the Sun during the collision? What happens to Earth? Let's trace the Sun's likely journey through the merger, based on the detailed simulations astronomers have run. The Sun currently orbits the Milky Way centre at a distance of about 26,000 light-years, taking roughly 230 million years to complete each orbit. We're moving at about 220 kilometers per second in our orbit, a speed that would carry us from Earth to the Moon in less than 2 hours. When Andromeda's approach becomes significant, perhaps 3 billion years from now, the Sun's orbit will begin to change. Andromeda's gravity will tug on us, altering our path slightly with each of our orbits around the galactic centre. The changes are subtle at first, but they accumulate over time. During the first close encounter with Andromeda, about 4.5 billion years in the future, the Sun will likely be pulled into a more elliptical orbit. We might find ourselves carried closer to the galactic centre on one part of our orbit and farther out on another. The orderly circular path we've followed for billions of years will become distorted. With subsequent collisions, our orbit becomes increasingly chaotic. We're tugged this way and that by the combined gravity of both galaxies' stars. We might make close approaches to massive star clusters. We might pass through regions of dense gas. Our velocity changes, our direction changes, our distance from the galactic centre fluctuates wildly. But through all this chaos, the simulation suggests that the Sun will likely be kicked outward, move to a greater distance from the merged galaxy's centre. The final simulations place our solar system about 40,000 to 50,000 light-years from Milkomeda's core, in a relatively sparse region of the new galaxy. This is actually fortunate in a way. The central regions of elliptical galaxies can be crowded, with stars packed closely together and supermassive black holes generating intense radiation. The outer regions are quieter, safer places for planetary systems. What about Earth itself? Here the news is less reassuring. Though not because of the galaxy collision. The problem is the Sun's own evolution. Our Sun is gradually growing hotter as it ages. In about 1 billion years, the Sun's increasing luminosity will make Earth uninhabitable. The oceans will evaporate. The atmosphere will be lost to space. Earth will become a scorched, dead world. By the time the collision with Andromeda begins in earnest, Earth will have been dead for billions of years, if it hasn't been completely destroyed. And about 1 billion years after that, roughly 5 billion years from now, the Sun will exhaust the hydrogen fuel in its core and begin its transformation into a red giant. It will swell to enormous size, its outer layers expanding to engulf the inner planets. Earth will almost certainly be swallowed by the expanding Sun, vaporized and incorporated into the Sun's outer atmosphere. If by some chance we survive even that, we won't survive long. Eventually the Sun will shed its outer layers completely, exposing its hot core as a white dwarf star. The planets that remain will orbit this stellar remnant in a cold, dark planetary system. So while the Sun will survive the galaxy collision and find a new home in Milkomeda, Earth will not. Our planet's fate is tied not to the collision of galaxies, but to the inevitable evolution of our own star. This might sound melancholy, but it's worth remembering the timescales involved. Humanity has existed for perhaps 300,000 years. Civilization for 10,000 years. In 1 billion years, if any descendants of humanity still exist, they will be so changed, so evolved, so different from us that we wouldn't recognize them. They might have spread to other stars long ago. They might have left biology behind entirely, existing as digital minds in constructed worlds. They might be something we can't even imagine. The end of Earth doesn't mean the end of whatever humanity becomes. Our story continues, even as the planet where we evolved returns to the cosmos. At the heart of the Milky Way, buried deep within a dense cluster of stars, lies a supermassive black hole. We call it Sagittarius A star, and it contains the mass of about 4 million suns, compressed into a region smaller than our solar system. It's the gravitational anchor of our galaxy, around which hundreds of billions of stars orbit. Andromeda has its own supermassive black hole larger than ours, containing perhaps 140 million solar masses. This vast gravitational monster sits at Andromeda's core, Invisible but powerful, its presence detected through the motion of stars orbiting nearby and through the faint radiation emitted by gas spiraling into its depths. When the Milky Way and Andromeda merge, these two black holes will eventually merge as well. It's an event almost too extreme to contemplate, the collision of objects so dense that they warp space and time itself into impossible curves. But it will happen, inevitably, as the final act in the galaxy's merger. The process begins when the two galaxies first collide. During the early encounters, the black holes are still separated by millions of light years, but with each pass, as stars are scattered and redistributed, the cores of both galaxies sink toward the centre of mass of the merged system. This sinking happens through a process called dynamical friction. As a massive object moves through a field of stars, it attracts them gravitationally. Stars behind it are pulled forward, gaining energy. Stars in front are pulled backward, losing energy. The net effect is that the massive object loses momentum and sinks inward, while the stars around it gain energy and move outward. Over hundreds of millions of years, both supermassive black holes spiral toward the centre of the forming elliptical galaxy. Eventually they find themselves just a few light years apart. Two gravitational leviathans circling each other in the core of Milkomeda. But here the process becomes more complicated. When the black holes are this close, dynamical friction becomes less effective. There aren't enough stars passing close enough to carry away the black hole's orbital energy. Astronomers call this the final parsec problem. The challenge of understanding how black holes make the final approach from a few light years of separation to actual merger. The leading theory involves gas. If there's enough gas in the galactic core, it can interact with the orbiting black holes, creating drag that pulls them together. Or perhaps the random gravitational kicks from passing stars, though individually small, might eventually push the black holes close enough to merge. However it happens, the end result is clear. At some point, the two black holes will approach so closely that they enter each other's gravitational grip. They'll begin spiraling inward rapidly, orbiting each other millions of times per second, moving at significant fractions of the speed of light. As they spiral inward, they'll create ripples in space-time itself, gravitational waves that carry energy away from the system. These waves, predicted by Einstein's theory of general relativity and first detected in 2015, will radiate outward through the universe at the speed of light. The final moments before merger will be spectacular, at least to instruments capable of detecting gravitational waves. The black holes will orbit each other faster and faster, releasing more and more energy in gravitational waves, until finally they merge in a cataclysmic event that creates a larger black hole and sends a final burst of gravitational waves propagating across the cosmos. The merged black hole will contain about 144 million solar masses, slightly less than the sum of the two original black holes. The missing mass, perhaps a few million solar masses worth, will have been converted to energy and radiated away as gravitational waves during the merger, and this new, larger black hole will settle into the centre of Milkomeda, becoming the gravitational heart of the merged galaxy, just as its two parent black holes were the hearts of their respective galaxies. From a great distance, from another galaxy billions of light years away, an advanced civilization with gravitational wave detectors might notice a brief signal passing through their instruments, a chirp lasting perhaps a few seconds, the signature of two black holes merging in a distant galaxy. And they might wonder, briefly, about the galaxies that collided to create that signal, about the stars scattered and reformed, about the worlds that might have witnessed the merger. For all the disruption of a galaxy merger, for all the scattered stars and distorted orbits, these collisions are also moments of creation. They trigger the birth of new stars on a scale that's difficult to comprehend. The mechanism is straightforward, even if the scale is not. Galaxies contain vast clouds of gas, mostly hydrogen and helium, spread throughout their disks. In a normal spiral galaxy, These clouds slowly collapse under their own gravity to form new stars, a steady process that can continue for billions of years. But when galaxies collide, the gas clouds from both galaxies smash into each other. Unlike stars, which pass through each other without touching, gas clouds actually collide. And when clouds of gas moving at hundreds of kilometers per second run into each other, they compress. Compressed gas heats up. The pressure increases. And if the compression is strong enough, regions within the gas clouds become dense enough that gravity takes over, pulling the gas into tight clumps that continue collapsing. These collapsing regions become nurseries where new stars are born. The star formation triggered by galaxy mergers can be prodigious. A normal galaxy like the Milky Way might create a few new stars per year, slowly converting its gas reservoir into stars over billions of years. But a colliding galaxy pair can create hundreds or even thousands of new stars per year, using up gas at a furious rate. We can see this process happening in colliding galaxies throughout the universe. Through powerful telescopes, we observe brilliant blue regions in merger systems, areas where massive young stars have recently formed. These young stars burn hot and bright, emitting ultraviolet radiation that makes them easy to spot. The most spectacular example might be the Antennae galaxies, two spiral galaxies about 60 million light-years from Earth caught in the midst of a collision. Through telescopes, they appear as a chaotic tangle of stars and gas, with two long tidal tails extending from the main merger, curved streamers of stars pulled out by gravitational forces. Hence the name. The tails look like an insect's antennae. But the most interesting features are the brilliant knots of light scattered throughout the merger. These are superstar clusters, regions where thousands or millions of stars have formed very close together. Each cluster contains more stars than typical star clusters in our galaxy, packed into a region just a few tens of light years across. These superstar clusters are windows into what might happen during the Milky Way Andromeda collision. When our galaxy's gas clouds collide, they too will create regions of intense star formation. New stellar systems will be born from the collision, planets forming around young suns, perhaps eventually becoming homes to life, to intelligence, to civilizations that will never know the separate galaxies their stars came from. There's something profound about this process. Galaxy collisions destroy the elegant spiral structures that took billions of years to form. They scatter stars from their orderly orbits. They create chaos from order, and yet from that same chaos comes creation, the birth of new stars, new possibilities. It's worth thinking about the stars that will be born during the Milky Way Andromeda merger. Some might form from gas that originated in the Milky Way, some from gas from Andromeda, and some from gas clouds where material from both galaxies is mixed together, truly hybrid stars belonging equally to both parent galaxies. These new stars will be rich in heavy elements, enriched by billions of years of stellar evolution in both galaxies. The gas clouds contain carbon and oxygen, nitrogen and iron, silicon and gold, all the elements forged in the cores of ancient stars and scattered by supernovae throughout both galaxies. The new stars will incorporate this chemical wealth, and the planets that form around them will be rich worlds, capable of chemistry complex enough for life. And perhaps, billions of years after the merger is complete, after Milkomeda has settled into its new form as an elliptical galaxy, some planet orbiting one of these stars will develop life. Perhaps intelligence will arise. Perhaps some being will look up at the stars and wonder about the history of their galaxy, about where it came from, about what cosmic events shaped the system that gave them birth. They might never know that their home galaxy was born from the merger of two spirals, that their sun was created in the chaos of collision, that their existence is a consequence of one of the universe's most fundamental processes, the constant transformation of structure, the endless dance of creation and destruction. There's a haunting question at the heart of this story. When Andromeda and the Milky Way finally collide, will there be anyone left to witness it? Will humanity, or whatever we evolve into, still exist to watch the greatest celestial spectacle in our galaxy's history? The honest answer is that we don't know. 4 billion years is an almost incomprehensible span of time. To put it in perspective, 4 billion years ago, Earth had only just finished forming. Life existed, yes, but only as simple single-celled organisms. The most complex living things were bacteria. There were no plants, no animals, no eyes to see with, no minds to comprehend. Everything we think of as life, everything that crawls and swims and flies and thinks, all of it evolved in the 4 billion years since then. And in another 4 billion years, an equal span of time will have passed. If evolution continues at roughly its historical pace, whatever exists on Earth in 4 billion years will be as different from us as we are from those ancient bacteria. But that assumes life continues on Earth at all. As we discussed earlier, Earth's habitability will end long before the collision. The sun's gradual brightening will make our planet uninhabitable in about 1 billion years. Long before galaxies collide, Earth will be a dead world. Yet this doesn't necessarily mean the end of our story. If humanity survives the next few centuries, if we navigate the challenges of climate change, nuclear weapons, artificial intelligence, and all the other potential catastrophes that loom in our near future, we might spread beyond Earth. We might colonize Mars, terraform it into a living world. We might build habitats in orbit around the Sun. Vast cylindrical worlds where millions could live in Earth-like conditions. We might send generation ships to other star systems, carrying our descendants to planets orbiting distant suns. If we do this, if we become a truly spacefaring species, then our descendants might still exist when the collision begins. They might watch from worlds we can't even imagine, orbiting stars whose names we don't yet know, as Andromeda's approach lights up the sky. But there's another possibility, perhaps more likely. We might transcend biology entirely. In 100 years, in 1,000 years, we might upload our minds into machines, becoming digital intelligences that don't require planets or biology to exist. We might merge with artificial intelligence, creating hybrid forms of consciousness that we can barely conceive of today. These digital descendants might exist for billions of years, far longer than biological organisms could survive. They might witness not just the Andromeda collision, but the entire future history of the universe. They might watch stars form and die, galaxies merge and fade, the universe itself grow old. Or perhaps we'll simply vanish. Perhaps we'll destroy ourselves in the next few centuries, another failed experiment in technological civilization. Perhaps we'll evolve into something that no longer cares about stars and galaxies. Perhaps we'll deliberately choose to end our existence, deciding that consciousness itself is too painful to maintain. The future is genuinely uncertain. We can predict the motion of galaxies billions of years in advance with reasonable confidence. The laws of gravity are well understood, and galaxies follow predictable paths. But we can't predict the future of intelligence, of consciousness, of whatever spark it is that makes us care about galaxies at all. What we can say is this: if any of our descendants exist 4 billion years from now, they'll witness something magnificent. They'll see a sight that humans have never seen, that perhaps no intelligent beings in our galaxy have ever seen. The slow-motion collision of two massive spiral galaxies. They'll watch Andromeda grow larger in the sky year by year. They'll see the first tidal distortions as the galaxy's outer regions begin to interact. They'll witness the first collision, when billions of stars from each galaxy thread through each other's disks. They'll see new stars being born in brilliant blue clusters. They'll watch the gradual transformation of two spirals into one elliptical galaxy. And perhaps, watching this cosmic dance unfold over millions of years, they'll think of us, their distant ancestors, who first predicted this collision, who first understood what was coming, who looked up at a faint smudge of light in the constellation Andromeda and realized it was falling toward us. Perhaps they'll remember that we cared about this, that we found it beautiful, that we tried to understand our place in this vast and ancient universe. 4 billion years. It's easy to write those words, to say them out loud, but it's nearly impossible to truly comprehend what they mean. The human mind wasn't designed to grasp timescales like this. Our intuitions about time are shaped by the rhythms of our own lives, by days and seasons and human lifespans. Let's try to build up to it slowly, to give our minds stepping stones toward understanding. A human lifetime, on average, lasts about 70 or 80 years. That's our basic unit of time, the scale we naturally understand. We can imagine our parents' lives, our grandparents' lives, perhaps even our great-grandparents' lives. 3 or 4 generations back, maybe 150 years, and we're already reaching the limits of personal connection. Go back 1,000 years, and we're in the Middle Ages. Castles and knights, the height of the Mayan civilization in the Americas, the Song dynasty in China. 1,000 years is beyond the reach of family memory, but we can still sort of grasp it through history. We can name events, remember dates, connect to that time through the stories we have inherited. 10,000 years brings us to the invention of agriculture, to the first permanent human settlements. Everything we think of as civilization, all our cities and technologies and accumulated knowledge, has happened in the last 10,000 years. 100,000 years encompasses all of modern human existence. Our species, Homo sapiens, arose somewhere between 200,000 and 300,000 years ago. 100,000 years is roughly the span of human consciousness as we understand it, of minds like ours looking up at the stars and wondering. 1,000,000 years is harder. 1,000,000 years ago, our ancestors were not yet fully human. They were earlier members of the Homo genus, with smaller brains, more primitive tools, no language as we would recognize it. 1,000,000 years is deep enough to take us beyond humanity itself. 10 million years, and we're not even primates anymore, at least not recognizable ones. Our ancestors were small, tree-dwelling creatures that would eventually give rise to monkeys and apes and humans, but they weren't any of those things yet. 100 million years ago, dinosaurs ruled the earth. Tyrannosaurus and Triceratops wouldn't evolve for another 30 million years. Our mammalian ancestors were tiny, probably nocturnal, hiding from the great reptiles that dominated the planet. 1 billion years is where things become truly alien. 1 billion years ago, Earth's continents were arranged completely differently. The atmosphere was different. Complex life existed, yes, but nothing like today. No fish, no insects, no plants on land at all. Just single-celled organisms and simple multicellular life in the oceans. And 4 billion years? 4 billion years is most of Earth's history. It's a span of time so vast that continents have formed and vanished. Entire oceans have opened and closed. The composition of the atmosphere has changed multiple times, and life has evolved from simple chemistry to everything we see around us. Now extend that same span forward. 4 billion years into the future. All of recorded human history, from the first cities in Mesopotamia to today, is less than 1/100th of 1% of that time. The age of dinosaurs, which lasted about 165 million years and seems impossibly long to us, would fit into that future span more than 24 times. Think about all the changes that can happen in such a vast expanse of time. Species rise and fall, mountains erode to nothing, new mountain ranges thrust up from the sea, continents drift across the planet's surface, the sun grows brighter, the universe expands. And through all of it, through this immensity of time that our minds can barely touch, Andromeda draws closer, slowly, patiently, inevitably. 100,000 kilometers closer with each passing million years, 400 kilometers with each 1,000 years. It seems like nothing against the vast distances involved, but it adds up steadily across the eons. When we say the collision will happen in 4 billion years, we're not making a statement about the near future. We're talking about an event separated from us by nearly the entire history of our planet. We're talking about a future as far ahead of us as the origin of life on Earth is behind us. And yet we can predict it. We can know it's coming. That, perhaps, is the real wonder. not the collision itself, but the fact that we, with our brief lives and limited minds, can peer so far into the future and see what's written there. The Milky Way and Andromeda aren't alone in the universe, of course. Everywhere we look, we see galaxies interacting, influencing each other, sometimes colliding. It's worth taking a moment to contemplate some of these other cosmic encounters, to see our own impending collision in the context of the universe's larger patterns. Perhaps the most spectacular example is a pair of galaxies called NGC 4038 and NGC 4039, though they're better known by their nickname, the Antennae Galaxies. We touched on them earlier, but they deserve a longer look. About 60 million light-years from Earth, in the constellation Corvus, two spiral galaxies are caught in the midst of a violent merger. They collided about 600 million years ago, their first encounter. And they're now in the chaotic phase where both galaxies' structures have been completely disrupted. Through telescopes, the Antennae Galaxies are breathtaking. Two long tidal tails extend from the merger, curved streamers of stars pulled out by gravitational forces during the collision. These tails stretch for hundreds of thousands of light-years, far beyond the original boundaries of either galaxy. They're called tails, but really they're like fossil records of the collision, showing the path the galaxies took as they passed through each other. Within the merger itself, brilliant blue knots mark regions of intense star formation. The collision has compressed vast gas clouds, triggering the birth of millions of new stars. Some of these star-forming regions are superstar clusters, containing hundreds of thousands or millions of stars packed into regions just tens of light-years across. The Hubble Space Telescope has captured extraordinary images of the antennae, showing individual star clusters, nebulae, and even some of the brightest individual stars. These images give us a preview of what the Milky Way Andromeda collision might look like from a distance, a chaotic but beautiful dance of destruction and creation. Much closer to home, we can observe the Magellanic Clouds, two small irregular galaxies visible from the southern hemisphere. The large and small Magellanic Clouds are satellite galaxies of the Milky Way. In orbit around our galaxy at distances of about 160,000 and 200,000 light-years respectively, these dwarf galaxies are slowly being pulled apart by the Milky Way's gravity. The Magellanic Stream, a vast river of gas stretching across much of the southern sky, is material stripped from the clouds by tidal forces. Eventually, in a few billion years, the Magellanic Clouds will merge with the Milky Way, adding their stars to our galaxy's population. Farther out, in the Virgo cluster of galaxies, we can observe dozens of galaxies interacting simultaneously. The cluster contains more than 2,000 galaxies packed into a region about 15 million light-years across. Many of these galaxies show signs of tidal distortions, evidence of close encounters with neighbours. Some are caught in the midst of mergers. One particularly striking example is Messier 87, a giant elliptical galaxy at the heart of the Virgo cluster. This massive galaxy has clearly grown through numerous mergers, cannibalizing smaller galaxies over billions of years. It's surrounded by a swarm of globular clusters, ancient collections of stars that might be the remnants of past mergers. And then there's the Bullet Cluster, one of the most important galaxy clusters in modern astronomy. About 3.5 billion light-years away, two galaxy clusters collided at enormously high speed. The collision separated the cluster's gas, which interacted and slowed down, from their dark matter, which passed through without interacting. This separation gave astronomers some of the strongest evidence for dark matter's existence. All these examples, from nearby satellite galaxies to distant cluster collisions, show us that galactic interactions are common throughout the universe. They're part of how galaxies grow and evolve. They're how structure develops on cosmic scales. The Milky Way Andromeda collision is just one more example of this universal process. We're not experiencing something unique or special. We're participating in the same dance that galaxies have been performing for billions of years, across billions of light-years of space. There's something comforting in that, isn't there? Our cosmic future is written in the patterns we see all around us. We know what's coming because we've seen it happen elsewhere. We're part of something larger, something ancient, something that connects our tiny corner of space to the grand sweep of cosmic evolution. There's a peculiar comfort in the slowness of cosmic processes. When we hear _quote, _0 our minds might jump to images of explosion, of immediate catastrophe. But the reality is gentler, stretched across timescales that make human lifetimes seem like fleeting moments. Consider what _quote, _1 means on these scales. Andromeda approaches us at about 110 kilometers per second. That sounds fast, and by human standards, it is. A car travelling at 110 kilometers per second would circle the Earth in less than 6 minutes. It's faster than any human-made object has ever travelled. But against the vast distance separating us from Andromeda, that speed is glacially slow. At 110 kilometers per second, it would take Andromeda about 680 years to cross a single light-year of space. To cross the entire 2.5 million light-year gap between us takes billions of years. Think about what this means for anyone who might witness the collision. You wouldn't see Andromeda noticeably move during your lifetime. You might notice it's larger than historical records suggest if you're paying careful attention and have access to precise measurements. But to the naked eye, from one year to the next, or even from one decade to the next, Andromeda would appear stationary. Even when the collision is imminent, when Andromeda fills half the sky, you could watch for an entire human lifetime and see almost no change. The galaxy might grow slightly larger. Some of its features might shift position minutely. But there would be no sudden moment, no instant when everything changes. This is true even during the most dynamic phases of the collision. When the two galaxies' disks pass through each other, when billions of stars from each galaxy thread through the space between stars in the other, it happens over millions of years. Individual stars don't suddenly appear in the sky. They fade in gradually, over timescales far longer than human civilization has existed. The spiral arms distorting, the tidal tails forming, the new stars being born in collision-triggered star formation regions, all of it happens slowly enough that no human observer would perceive it as motion. You'd need to compare observations separated by thousands of years to see the changes. There's something almost meditative about this pace. The universe operates on timescales that dwarf human experience, that make our urgencies and anxieties seem almost comically brief. We rush through our days, worried about deadlines and schedules, while above us galaxies drift toward their meetings across billions of years. This slowness also means there's no moment of danger, no instant when everything goes wrong. If humanity or its descendants still exist when the collision occurs, they'll have millions of years of warning. They'll see it coming from so far away that there will be time to prepare, to adapt, to move if necessary. Not that moving would be necessary. As we've discussed, the collision won't directly threaten planets or solar systems. But if for some reason it became desirable to relocate, there would be time to build generation ships and send them to other stars. Time to develop new technologies for space travel. Time to carefully, thoughtfully, deliberately respond. Compare this to the dangers we face now. Climate change is slow by human standards, but catastrophically fast by cosmic standards. We have decades to respond, not billions of years. Nuclear war could devastate the planet in hours. An asteroid impact would give us weeks or months of warning at most. The threats we actually face are immediate, pressing, urgent. The galaxy collision, by contrast, is almost absurdly gentle. It's like being told that in billions of years, after a journey spanning most of the lifetime of the Earth, after so much time that life will have evolved into forms we can't imagine, two galaxies will slowly, gradually, gently merge. There's a profound lesson in this about perspective. The things that seem catastrophic on cosmic scales, the events we describe with dramatic language like quote 2 and quote 3, are actually incredibly gentle when experienced on human timescales. And the things that seem minor on cosmic scales, the tiny fluctuations in a planet's atmosphere or the brief burning of nuclear weapons, those can be catastrophic on human timescales. The universe doesn't operate on our schedule. It has its own rhythms, its own pace, vast and slow and patient. Andromeda is coming, yes, but it's coming so slowly that slow itself becomes a kind of peace. Let's imagine the sky as it might appear during the collision, the view from Earth or from whatever worlds our descendants might inhabit. It's worth painting this picture carefully, because it's one of the most beautiful aspects of this cosmic merger. Today, on a dark night far from city lights, the Milky Way appears as a faint band of light across the sky. It's the combined glow of billions of stars in our galaxy's disk, seen from our position within that disk. It's beautiful. Though many people living in modern cities have never seen it, have never experienced a truly dark sky. Andromeda, by contrast, appears as a small fuzzy patch, visible to the naked eye but not impressive. You need to know where to look and what to look for. Through binoculars or a small telescope, it's more interesting, showing an oval shape with a bright core, but it's still just one object among many in the night sky. Now imagine the sky 2 billion years from now, halfway through the approach. Andromeda has grown. It's no longer a small fuzzy patch, but a definite spiral galaxy, visible to the naked eye with clear structure. You can see its central bulge. You can see its spiral arms. It's still smaller than the Milky Way's band across the sky, but it's becoming a prominent feature. The constellations are still roughly recognizable at this point, though stars have drifted slightly in their positions due to their own motions through space. The familiar patterns of Orion, Ursa Major, Cassiopeia, they're all there, changed but not unrecognizable. 3.5 billion years from now, Andromeda dominates. It's grown from a small oval to a vast spiral spanning many degrees of sky. Its structure is clear and detailed. You can see dark dust lanes threading through its spiral arms. You can see bright star-forming regions scattered throughout. It's magnificent, rivaling the Milky Way itself in its grandeur. The constellations are starting to break down now. Stars have moved enough that the familiar patterns are distorted. New patterns might emerge, but the sky our ancestors knew is fading. At 4 billion years during the first close approach, the sky becomes genuinely alien. Andromeda fills perhaps a third of the visible sky, its spiral arms stretching in graceful arcs overhead. The galaxy is bright enough to cast faint shadows on a moonless night. Its core glows like a second Milky Way, a vast concentration of stars visible even through city lights. But it's not just Andromeda that's changed. The Milky Way itself looks different, distorted by Andromeda's gravity. The familiar band of light is warped, stretched in some areas, compressed in others. New clusters of bright blue stars mark regions where the gravitational interaction has triggered star formation. During the actual collision, when the two galaxies' disks pass through each other, the sky becomes a chaos of light. There's no longer a clear distinction between the Milky Way and Andromeda. Instead, the entire sky is filled with stars, billions upon billions of them, from both galaxies mingled together. Imagine looking up and seeing not one band of light but multiple streamers, great arcs and tails of stars stretched across the heavens. Imagine seeing superstar clusters, each one brighter than any star cluster in today's sky, scattered throughout this cosmic tapestry. Imagine seeing the night sky not as a dark canvas with points of light, but as a luminous cathedral, glowing with the combined light of 1 trillion suns. And yet, even at the peak of the collision, individual stars would still appear as points of light. You wouldn't see them moving, wouldn't perceive the vast dance happening on scales too large and too slow for human perception. You'd see a beautiful alien sky, but you'd still see individual stars, still see patterns, still see the universe spread out above you. Eventually, over hundreds of millions of years, the sky would settle. the chaotic merger would resolve into a new configuration. The tidal tails would fade as their stars dispersed. The intense star formation would slow as gas was exhausted, and eventually, perhaps 1 billion years after the final merger, the sky would stabilize into its new form. What would it look like then? Probably more uniform than today, without the distinct band of the Milky Way. More like the sky you'd see from a planet orbiting a star in an elliptical galaxy, with stars distributed more evenly in all directions. Different, but still beautiful. Still a sky worth looking up at. Still a reminder of our place in this vast cosmos. Astronomers have already named the galaxy that will result from this merger, even though it won't exist for billions of years. They call it Milkomeda, a simple portmanteau of Milky Way and Andromeda. Sometimes it's called Milkdromeda, or even just the Andromeda-Milky Way merger. But Milkomeda has a certain poetry to it, a recognition that this new galaxy will be the child of both parents, belonging equally to each. What will Milkomeda look like? Computer simulations give us a good idea. It will probably be an elliptical galaxy, shaped something like an elongated sphere or a cosmic football. The beautiful spiral arms of both parent galaxies will be gone, their orderly structure lost in the chaos of the merger. Elliptical galaxies are different from spirals in fundamental ways. Spirals like the Milky Way and Andromeda are relatively flat, with most of their stars orbiting in roughly the same plane. They're organised, structured, with clear rotation. Ellipticals are more chaotic. Their stars orbit in all directions, with no preferred plane, no clear sense of rotation. They're three-dimensional in a way that spirals are not. This difference in structure affects everything about the galaxy. Star formation in ellipticals is typically much lower than in spirals, because ellipticals contain less gas. During the merger, much of the gas will be used up in bursts of star formation. Some will be heated to such high temperatures that it escapes the galaxy entirely, blown out by stellar winds and supernova explosions. What remains won't be concentrated in a disk where it can easily form new stars, so Milkomeda will likely be a relatively quiescent galaxy, producing few new stars. Most of its stellar population will be old, the stars that existed in the Milky Way and Andromeda before the merger, plus those born during the merger itself. These stars will age gradually, turning from bright blue and white to yellow, then orange, then red, and finally fading to white dwarfs. The colour of Milkomeda will shift over time. Young, immediately post-merger, it might have a bluish tint from all the massive young stars born during the collision. But gradually, as these short-lived massive stars die, the galaxy will redden. Old elliptical galaxies glow with a yellowish or reddish light, the combined emission of billions of old, cool stars. The size of Milkomeda is impressive to contemplate. It will be larger than either parent galaxy, containing all the stars from both. Astronomers estimate it might span about 200,000 light-years or more, nearly twice the size of the current Milky Way. It will contain perhaps 800 billion to 1 trillion stars, making it one of the larger galaxies in our cosmic neighbourhood. At its centre will be that merged supermassive black hole we discussed earlier. A gravitational monster of about 144 million solar masses. This black hole might go through a period of intense activity after the merger, feeding on gas and stars that sink to the galactic centre, possibly shining as a quasar for a time. But eventually it will settle down, becoming relatively quiet like the black holes at the centres of most nearby galaxies. The galaxy's outer regions will be sparse, with stars scattered at greater distances than in today's Milky Way. Our Sun, if it still exists, will likely be out there, orbiting in the quieter suburbs of the new galaxy. It's a peaceful thought, actually, flung to the outskirts by the merger's chaos, but finding a stable orbit in a region where encounters with other stars are rare, and Milkomeda won't be alone. The other galaxies of the local group, the smaller ones like the Triangulum galaxy and the various dwarf galaxies, will still be there. Some might merge with Milkomeda eventually, Others might be flung away by gravitational interactions during the collision, but there will still be a local neighbourhood, still be cosmic companions orbiting in the darkness. In some sense, Milkomeda represents an ending, the death of two ancient spiral galaxies. But it also represents a beginning, the birth of a new galaxy that will continue existing for billions of years, home to whatever stars and worlds and perhaps even intelligences persist or arise in the deep future. It's a transformation, not an ending. A change in form, but a continuation of existence. The matter that makes up the Milky Way and Andromeda won't be destroyed. It will be rearranged, reformed, made into something new. And that new form will have its own beauty, its own story, its own slow evolution across the remaining lifespan of the universe. While Andromeda and the Milky Way are drawing together, the universe as a whole is expanding, carrying distant galaxies away from us at ever-increasing speeds. It's a profound paradox, this simultaneous approaching and receding, and it's worth spending some time contemplating what it means for the cosmic future. The expansion of the universe was discovered in the late 1920s by Edwin Hubble, the same astronomer who first measured the distance to Andromeda. Hubble observed that most galaxies are moving away from us, and that the farther away a galaxy is, the faster it's receding. This relationship between distance and recession velocity is called Hubble's law. At first, astronomers thought the expansion might be slowing down, that gravity would eventually halt it and perhaps even reverse it, causing the universe to collapse back in on itself in a big crunch. But observations in the late 1990s revealed something unexpected. The expansion is accelerating. Distant galaxies are receding faster now than they were in the past. This acceleration is driven by something we call dark energy, a mysterious force that permeates all of space and pushes everything apart. We don't understand what dark energy is any better than we understand what dark matter is. We just know it exists because we can measure its effects. Dark energy makes up about 68% of the total energy content of the universe. Dark matter accounts for about 27%. Everything else, all the normal matter that makes up stars and planets and us, represents only about 5%. We live in a universe dominated by things we don't understand. Because of dark energy, the universe will continue expanding forever. Distant galaxies will continue receding from us, moving away faster and faster as time passes. Eventually, galaxies more than a few billion light-years away will be receding faster than light can travel. Not because they're moving through space faster than light, which relativity forbids, but because space itself is expanding between us and them. When galaxies recede faster than light, their light can never reach us. They effectively disappear from our observable universe. They're still there, still existing, but we can never see them, never communicate with them, never interact with them in any way. This process has already begun. Right now, there are galaxies we can see whose light is redshifted to such an extent that we know we're seeing them as they were billions of years ago, and we'll never see what they look like today. Their current light will never reach us because space is expanding too fast, and this will continue. Over the next 100 billion years, more and more galaxies will disappear beyond our cosmic horizon. Eventually, only the galaxies gravitationally bound to Milkomeda will remain visible. The local group, or what's left of it after mergers, will be all that future astronomers can see. Imagine astronomers trillions of years in the future, looking up from some planet orbiting some star in Milkomeda. They'll see their own galaxy, perhaps a few small satellite galaxies orbiting it, and beyond that, nothing. The universe will appear to be just one galaxy surrounded by empty darkness. They might develop theories about how their galaxy formed, how the universe began. But they'll have no evidence of the wider universe, no way to see the billions of other galaxies that exist beyond their cosmic horizon. They'll live in a universe that appears much smaller and lonelier than the one we see today. We're actually living in a special time, cosmically speaking. We can see the full richness of the universe, billions of galaxies spread across billions of light years. We can observe the cosmic microwave background radiation, the afterglow of the Big Bang. We can study how the universe has evolved over cosmic time. Future civilizations won't have that privilege. The expansion of the universe will have hidden most of the cosmos from them. They'll have to infer its existence indirectly, through subtle clues and careful reasoning, or they might never know at all. So while Andromeda approaches us, while our local cluster of galaxies draws together through gravitational attraction, the rest of the universe is receding into darkness. We're gathering into islands of matter while the ocean of space expands around us, carrying other islands further and further away until they vanish beyond the horizon of light itself. It's melancholy in a way, this slow isolation, but there's also something peaceful about it. The local neighbourhood drawing together while the rest of the universe goes its own way, each island of matter left to its own evolution, its own story, its own fate. Let's extend our gaze even further into the future, past the collision, past the formation of Milkomeda, into the deep cosmic time when the universe itself grows old. Because the story of Andromeda's approach is just one chapter in a much longer story about the evolution of everything. Star formation cannot continue forever. Stars are made from gas, primarily hydrogen, and there's only so much hydrogen in the universe. Each generation of stars fuses hydrogen into helium and heavier elements. Eventually, the supply of raw hydrogen runs out. In the current universe, about 13.8 billion years after the Big Bang, star formation is already slowing down. The peak of star formation happened about 10 billion years ago. We're living in a universe past its prime, where the birth rate of stars is declining. This decline will continue. Over the next few trillion years, galaxies will exhaust most of their gas. Star formation will slow to a trickle, then stop entirely. The last stars will be born perhaps 10 trillion to 100 trillion years in the future, depending on how efficiently galaxies can gather and use their remaining gas. After that, no new stars will form. The universe will be left with whatever stars already exist, and these will gradually die. Massive stars will die first, exploding as supernovae or collapsing into black holes. They live fast and die young, lasting only millions of years. Medium-sized stars like our Sun live longer, burning for billions of years. The Sun itself will last about 10 billion years total. Stars smaller than the Sun can last even longer, burning their fuel so slowly that they might persist for trillions of years. The smallest stars, red dwarfs with just a fraction of the Sun's mass, are the most miserly. They burn so slowly that not a single red dwarf that has ever been born has yet died. The oldest ones, formed shortly after the Big Bang, are still shining today and will continue shining for trillions of years to come. These tiny red dwarfs will be the last lights in the universe. Long after the Sun has died, long after all the massive bright stars have burned out, the red dwarfs will still be glowing. Feeble and dim but persistent. They'll outlast everything. The tortoises in a cosmic race where slow and steady really does win. Eventually, though, even the red dwarfs will exhaust their fuel. The last stars will flicker and fade, becoming white dwarfs, stellar remnants that cool slowly over incomprehensible spans of time. The universe will enter the degenerate era, as cosmologists call it, a time when the only sources of light are these cooling embers of dead stars, along with any brown dwarfs and black holes. White dwarfs cool slowly, incredibly slowly. It takes trillions of years for a white dwarf to radiate away its heat. And even as they cool, they'll still be there, still existing, just gradually approaching the temperature of the cosmic microwave background radiation. Beyond that lies the black hole era, when even white dwarfs have faded to darkness, and the only significant objects are black holes. These will be strange times if time still has meaning in such a sparse universe. Black holes evaporate through Hawking radiation, but so slowly that even a stellar mass black hole might last 10 to the 100 power years to evaporate. Supermassive black holes like the one that will sit at the centre of Milkomeda will last even longer, perhaps 10 to the 110 power years or more. For unimaginable spans of time, these black holes will be the last remnants of galaxies, slowly evaporating into the darkness, and finally, in the deep dark era, even the black holes will be gone. The universe will be filled with a thin soup of elementary particles, photons and neutrinos and whatever other stable particles exist, all at essentially the same temperature, just slightly above absolute zero. Nothing will happen anymore. Time will become meaningless in a universe where no change occurs. This is the ultimate fate of everything. The heat death of the universe predicted by thermodynamics. It's so far in the future that the numbers become meaningless. 10 to the 100 years is already more than a trillion times the current age of the universe. And we're talking about timescales far longer than even that. The collision of Andromeda and the Milky Way, happening just a few billion years from now, is an event in the universe's early history, cosmically speaking. We're living near the beginning of the story, not the end, in a time when galaxies still collide, stars still shine, and the universe is still dynamic and changing. There's a tendency when discussing cosmic events like galaxy collisions to frame them as catastrophes, as endings, as things to fear or mourn. But perhaps there's another way to think about it. A perspective that finds beauty in transformation itself rather than only in static perfection. The Milky Way as we know it will end. That's true. The beautiful spiral galaxy we live in, with its graceful arms and organised structure, will be destroyed in the merger. If we could preserve it somehow, keep it as it is forever, perhaps we would. There's something to mourn in the loss of that beauty. But transformation isn't the same as destruction. The matter that makes up the Milky Way won't cease to exist. The stars won't vanish. They'll be rearranged, incorporated into a new structure, a different kind of beauty. And that new structure will have properties and features that the old one didn't have. Elliptical galaxies like Milkomeda will have their own elegance. They're more three-dimensional than spirals, with stars orbiting in all directions, creating a kind of cosmic dance that's more complex and intricate than the orderly rotation of a spiral. From certain perspectives, they can be quite beautiful, glowing spheres of golden light in the darkness of space. And the merger will create things that couldn't exist otherwise. Those superstar clusters born in the collision, vast gravitationally bound groups of hundreds of thousands or millions of stars, are spectacular objects. They're much more impressive than the star clusters we see in the Milky Way today. They represent creation, new structure emerging from chaos. There's also something profound about the fact that change is possible at all, that the universe isn't static but dynamic, constantly evolving. A universe where nothing ever changed would be a dead universe, a cosmic museum where everything stays the same forever. That might sound peaceful, but it would also be sterile, empty of possibility. Change means that new things can emerge, that the future might be different from the past. It means that beauty can take new forms, that structure can reorganize itself, that endings can also be beginnings. Think about it from the perspective of the stars themselves, if stars could have perspectives. A star born in the Milky Way has spent its entire existence as a citizen of that galaxy, orbiting its core in a predictable path. But after the merger, that same star will be part of something larger, will have neighbours it never had before, will see the universe from a different position. Stars from Andromeda, from a completely separate galaxy with its own distinct history, will become siblings to our Sun, part of the same galactic family. There's something beautiful about that unity, about separate histories converging into a shared future. Or consider the new stars that will be born during the merger. They're not losses or endings, they're pure creation, new suns that wouldn't exist without the collision, potentially orbited by new planets, new worlds, new possibilities for chemistry and perhaps even life. These new stars will be rich in heavy elements, enriched by billions of years of stellar evolution in both parent galaxies. The worlds that form around them will have access to all the elements needed for complex chemistry, for water and carbon, and all the building blocks of life as we understand it. And who knows what might happen on those worlds? We can't predict the future of life, of consciousness, of whatever forms intelligence might take billions of years from now. But the collision creates opportunities, new environments where evolution can experiment, new cosmic neighborhoods where complexity can arise. There's also a kind of cosmic justice in all of this. Nothing is permanent, not even galaxies. The structures we see are temporary, lasting for billions of years perhaps, but temporary nonetheless. And there's honesty in that impermanence, a truth about the nature of existence. We are, all of us, part of this same process. Our bodies are made of elements forged in ancient stars, scattered by supernovae, incorporated into new generations of stars and planetary systems. We're recycled stardust, temporary arrangements of matter that will eventually be rearranged into other forms. The galaxy merger is just this same process on a grander scale. Stars and gas rearranged into new configurations. Structure reorganizing itself. The ongoing dance of matter and energy and gravity that has been happening since the Big Bang and will continue until the universe grows cold and dark. There's peace in accepting this, in finding beauty not in permanence, but in the transformations themselves, in the eternal dance of creation and destruction and recreation that defines the cosmos. We've travelled far in this exploration, from the discovery of Andromeda to the deep future of the universe itself. It's time to bring our journey home, to reconnect this cosmic scale to our human experience, to find meaning in these vast processes. When you look up at the night sky and see that faint smudge of light that is Andromeda, you're seeing something precious. You're seeing light that has travelled 2.5 million years to reach your eyes. You're seeing a galaxy containing 1 trillion stars, a structure so vast that light takes 220,000 years to cross from one side to the other, and you're seeing our future. You're seeing the galaxy that will one day merge with our own, that will transform the cosmic neighbourhood we call home, that will create something new from the combination of 2 ancient stellar islands. There's something deeply moving about that connection, about the fact that we can look up and see our cosmic destiny written in the stars. We know what's coming, we understand the process, and we can contemplate it with wonder rather than fear. This knowledge is a gift of modern astronomy, of science, of the human drive to understand our place in the universe. 1,000 years ago, no one knew what Andromeda was. 500 years ago, we thought it was a small cloud within our own galaxy. 100 years ago, we just discovered it was a separate galaxy but didn't know it was approaching. Now we know. We can predict the collision billions of years in advance. We can simulate it on computers. We can see the same process happening in other galaxies throughout the universe. We can understand our cosmic future with a clarity that would have seemed impossible just a few generations ago. And what we've learned is that the universe is both grander and gentler than we imagined. Grander in its scale, in the vast distances and long time scales and enormous energies involved, but gentler in its pace, in the slow working of gravity across the eons, in the way that change happens gradually enough that there's always time to adapt. We've learned that our galaxy isn't permanent, that it's just one phase in a longer cosmic story. We've learned that collision doesn't mean destruction, that galaxies can merge and create new structures. We've learned that we're part of a universe that's constantly transforming, always changing, never static. And we've learned something about ourselves, about the remarkable fact that we, tiny beings on a small planet orbiting an ordinary star, can understand these cosmic processes. We can reach out with our minds across billions of years and billions of light years. We can comprehend our place in space and time. That comprehension is perhaps our greatest achievement as a species. Not our technology, impressive as it is, not our art or our cities or our civilizations, but our understanding, our ability to look at the universe and figure out how it works, to peer into the past and predict the future, to know where we came from and where we're going. We are the universe become conscious of itself, as the cosmologist Carl Sagan once said. We are matter and energy temporarily organized in such a way that we can contemplate matter and energy. We are stardust that has learned to wonder about stars. And when Andromeda and the Milky Way merge, when our galaxy transforms into Milkomeda, we or our descendants or whatever we become will still be part of that same universe, still made of the same stardust, still capable of looking up and wondering. The collision doesn't change our fundamental nature. It doesn't alter the fact that we're part of this cosmos, participants in its evolution, witnesses to its grandeur. It just gives us a new galaxy to call home, a new cosmic neighborhood to explore and understand. So when you look up at Andromeda tonight, if the sky is clear and you can find it, don't think of it as a threat or a catastrophe approaching. Think of it as our cosmic companion, dancing with us through the darkness, drawing closer over billions of years to eventually join with us in creating something new. Think of it as a reminder that we're part of something larger than ourselves, larger than our planet, larger than our species, larger than anything we can easily comprehend. We're part of the cosmos itself, children of the stars, at home in this vast and ancient universe. And that is perhaps the most comforting thought of all. We belong here. This is our home, this cosmic dance of galaxies and stars. We're not separate from it, but part of it, woven into the very fabric of space and time. The universe is our home, and it always will be, no matter how it changes, no matter how it transforms, from now until the last stars fade and the universe itself grows quiet and cold in the deep cosmic future. We've travelled together for quite a journey tonight, haven't we? 2.5 hours wandering through deep time and vast space, contemplating the slow approach of Andromeda and the eventual merger that will transform our cosmic home. Thank you for staying with me through all of it, through billions of years of cosmic history and billions more of cosmic future. From the discovery of Andromeda as a separate galaxy to the realization that it's approaching us. From understanding the mechanics of galaxy collisions to contemplating the birth of Milkomeda, we've traced a story that spans nearly the entire lifetime of our planet. We've seen how galaxies drift together across billions of years, how they merge and create new stars, how they transform and continue in different forms. The answer to the question we began with, whether Andromeda is really coming and whether it's bigger than we thought, is yes to both. It's approaching at 110 kilometers per second, and it's far larger than early estimates suggested, with a halo extending perhaps 2 million light-years from its core. We're already, in a very real sense, touching Andromeda's outer edges, and in about 4 billion years, the two galaxies will merge completely, creating Milkomeda, a new elliptical galaxy that will be home to whatever stars and worlds and intelligences exist in that distant future. But perhaps what we've really discovered is something deeper. We've found that cosmic catastrophes aren't catastrophic at all when viewed on their actual timescales. We've learned that transformation can be beautiful even when it means the end of familiar structures. We've seen that the universe is constantly changing, always has been, always will be, and that this change is part of what makes existence meaningful, rather than something to fear. If you enjoyed this slow drift through cosmic time, a like and subscribe helps reach others who might find peace in these explorations of the universe. And to those of you who've been here before, who've joined me on other journeys through space and time, thank you. Your presence makes these long nights of cosmic contemplation feel less solitary. Wherever you are in the world right now, whatever time it is where you're listening, I hope you're comfortable. I hope your breathing has slowed. I hope your thoughts have quieted. I hope your body feels heavy and warm, ready for rest. We've spent 2.5 hours together contemplating the grandest scales of space and time, and you've earned some peace. Look up at Andromeda, if you can, if you know where to find it in your sky. Or just imagine it, that faint smudge of light that's actually a massive galaxy containing 1 trillion stars, approaching us across the void at 110 kilometers per second. Picture those spiral arms, so much larger than anyone realized until recently, reaching across millions of light years toward our own galaxy. Imagine the slow dance that's already begun. The gravitational pull that's been drawing these two galaxies together for billions of years and will continue for billions more. All those stars, hundreds of billions in each galaxy, each one potentially surrounded by planets, each planet a unique world with its own geology and chemistry and perhaps even life. All of them drifting together in the darkness, bound by gravity into these vast spiral structures that we can see across impossible distances. And billions of years from now, when the merger is complete, when Milkomeda glows in the night sky of whatever world still exist, perhaps some being will look up and feel the same sense of wonder we feel now. Perhaps they'll contemplate the history of their galaxy, unaware that it was born from the union of two spirals. Or perhaps they'll know, will have somehow preserved the knowledge across the eons, and will remember this time, our time, when the galaxies were still separate, still approaching, their merger still in the future. The universe is so much larger than we are, so much older, so much grander, and yet here we are, able to comprehend it, able to understand our place in it, able to look billions of years into the future and know what's coming. That might be the real miracle, not the collision itself, but our ability to understand it, to contemplate it, to find meaning in it. Sleep well. Dream of spiral galaxies drifting through the darkness, of stars being born in collision-triggered clouds of gas, of the slow, patient working of gravity across billions of years. Dream of transformation and continuity, of endings that are also beginnings, of the eternal dance of matter and energy across the cosmos. Dream of Andromeda approaching, growing larger in the sky, until one day the two galaxies are no longer separate but merged into something new and beautiful. Good night. Rest in the knowledge that the universe is vast and ancient and patient, that cosmic processes unfold over timescales that make human worries seem wonderfully, peacefully brief. The galaxies will keep dancing their slow dance, whether we're awake or asleep. Let them dance while you rest. Good night. And may the stars watch over you, both those in our own galaxy and those in Andromeda, all of them shining across the darkness, all of them part of the great cosmic story that includes us, that includes you, that includes everything. Good night.